Hello everyone, my name is Apoul and my colleague is Muwanguzi, and we are going to present a system that predicts the coffee yield production. So as the name suggests, contrastive attention-based knowledge distillation for coffee yield estimation using capsule networks. So in Uganda, as we all know, coffee is one of the most exported crops, as we can see from this graph. So that graph was extracted from the Uganda Coffee Development Authority, and it shows the coffee that has been exported from October 2023 to September 2024. The green bar shows the quantity or the amount of coffee that has been exported, and then the value is the red bar in US dollars. Now, what we are seeing next down there is the method that was used to calculate the amount of coffee by farmers, which was the traditional method, and that is what we call extrapolation method. That was ineffective. So when we go to our keywords or our key terms, we talk of knowledge distillation. This is a machine learning technique that aims to transfer the learning of a large pre-trained model, that is what we can call a teacher model, to a small student model. So contrastive learning, on the other hand, is a machine learning approach aimed at learning meaningful representations by contrasting pairs of either positive or negative. And we are going to use it in our system in this case, that is to differentiate or to distinguish between different types of coffee cherries in terms of unripe, ripening, and ripe, based on the visual features such as the colors, and the colors we are going to present in green for unripe, yellow for ripening, and then the red for the ripe one. So when we go to the next one is the attention mechanism. Well, as the name suggests, attention. So it's a technique used in machine learning and neural language processing to increase model accuracy by focusing on the relevant data. It will enhance the model's ability to focus on the key visions, that is the cluster of coffee cherries, leaves, canopy, and only action. That is what we are basing on for this case. So when we go to the next term, that is yield predictive analysis. Now, this is it is the use of data and advanced analytical techniques to predict outputs of planting a certain crop. We are talking of coffee in this case. So the model will help predict the coffee yield by analyzing the number and health of cherries, canopy, density, and leaf coverage. So we can now go to what we call the capsule neural network. This is an artificial neural network in machine learning designed to emulate hierarchical relationships, drawing inspiration from the organizational principles of biological neural structures. So we now go to the last one, which is the precision agriculture. Well, precision agriculture in this case is just we implement the technology in agriculture. Simple. Like, for example, we are now using AI to enhance the coffee yield estimation in our system. That is how it actually works. So when we go to our next one, which actually deals with the techniques that were used to estimate, or let us say for modeling complex agricultural data, we talk of that is the support vector machines, and then we talk of random forests, which are effective for modeling complex agricultural data sets. So although deep learning is outperforming them, deep learning is also having other data imperfection where the data is inaccurate, incomplete, and has bias outliners and some noise. So another challenge that we're actually facing in deep learning is feature selection is also a problem. For example, in the SVR that is about to deal with nonlinear data, but can focus on the key features. As we can all see in the graph here, that is the graph of the SVR, and it is having what we call decision boundaries. And then the data within the decision boundaries is what we are working on, and that data is actually separated by what we call hyperplanes. So when we go to our next slide, we're actually talking of our problem statement. So our problem statement in this case, we generated it from manual yield estimation, lacking standardization, leading to inconsistent yield prediction and poor resource allocation. So in this case, we can talk of, let's estimate in the next few years, Uganda's population is growing rapidly, and some of these things that population will have to be sustained by agriculture. And then that means we have to implement this system of ours so that we gain higher yields, so that we can predict the amount of yields that will sustain that population in simple terms. So these approaches, the approach which was being used currently lacks standardization and protocols, leading to inconsistent predictions, inaccurate planning, and inefficient resource allocation at times. So without reliable data, farmers struggle to make informed decisions affecting not only their productivity, but also their profitability. Thank you. Let me allow my colleague to take over for the next part.
Hello, my name is Muwanguzi, and I'll be talking about our system. So our proposed solution is to use mainly 4 key concepts. We have the knowledge distillation, as you see in the image above, where we are going to train the teacher model to learn from the data, and whatever knowledge the teacher model would have gotten, it will be passed on onto the student model that will be more efficient and reliable. This will ensure faster processing and more accuracy of the model. Then we have capsule networks. Why we chose to use capsule networks is because they preserve spatial relationships in images, which convolutional networks do not. And they're going to reduce the false detection, which is caused by the overlapping of the cherries in terms of the yield prediction. Then we have the attention mechanism. As you see in the picture on your right-hand side, the attention mechanism is to direct the model to focus on the coffee cherries, on the canopy, and on the contours of the leaf to ensure that better classification of ripeness is attained. Looking into our data, we obtain our data from Manly and RoboFlow. Our data is of the size from 10 MBs to 12 MBs with dimensions of 4,000 by 3,200 pixels with a resolution of 72 dots per pixel. Our data has instances of unripe, ripe, I beg your pardon. Our data has labels of unripe, ripening, and ripe, in addition with coffee tree. And those are the instances, as you can see on the table, with class IDs from 0 to 4. We performed an EDA and got the graph and were able to see how much of the yellow cherries, red cherries, and green cherries are in the data set of one bunch. How we plan to implement this model: we plan to carry out data collection, which we already did by getting the data from RoboFlow and Manly. Then we performed a data processing, the exploratory data analysis, where we obtained this graph that is showing the leaf count versus the coffee cherry count by ripeness. And then we are going to train the model to learn from these images. And after, we shall evaluate to see if the model actually is able to predict the yield. And then thereafter, we shall deploy this model in the different farms in Uganda. What we expect from this model is improved yield estimation so that the farmers can be able to make right decisions. And we expect that there will be less costs and there will be reduction in the labor that is needed to count the coffee. In the future, we plan to expand this model to other crops, and we hope to integrate IoT-based sensors. However, we expect some limitations in the model architecture complexity. The capsule networks, they work in a way where you need multiple layers to capture the spatial hierarchies. But if we keep on increasing these layers, that means you're going to face computational inefficiency, and that means you're going to need more memory, and that will require us to get computers that have GPUs. And we also expect to face a problem of knowledge distillation, where we have to ensure that the teacher and the student framework are aligned properly. But with this alignment comes a problem of compressing the model. And we cannot compress the model because there is risk of losing crucial information. Yes, thank you. That's all for the project.